The last speaker for this session will be Morris from Tel-Aviv University.
Cool. So thank you. Thank you for the invitation. And thanks to all the speakers who came before. So I'm going to be talking about an ongoing project that I'm doing in collaboration with Dr. Shai Gordon, which we're calling Deeplomatics. Now, Deeplomatics is kind of a pun. So actually, Shai taught me the word diplomatics, which is related to the English word diploma, and it deals with the study of the form of ancient documents. In our case, we're looking at applying deep learning in order to better understand the form and the contents of cuneiform documents. I think this is a really cool collaboration, and it's kind of using skill sets both from Assyriology, which is something I think is super interesting, even though I don't pretend to be an expert in it, and deep learning, specifically both computer vision and NLP. So that's what I'll be talking about. Okay, so I want to first just introduce us. I'll talk a bit about cuneiform. I don't think I need to say a lot because I think most people here know something about it, but I'll say a bit about why I think this is interesting. And then I'll introduce the ongoing task that we're working on within the framework of this project, Deeplomatics. So that's what I'll be talking about in the time that I have. Okay, so first just a bit about us. This is actually slightly out of date because I just finished my master's and I'm actually continuing to a PhD in electrical science here at Tel-Aviv University. And I'm really interested in multimodal learning, so combining computer vision with NLP and other structured sources of data. This project, Deeplomatics, is a collaboration that I've been doing with Shai for a while now. And as I said, I think it's a really cool combination of the best of both worlds. So let me just give a brief intro. I won't dwell on it. Again, I don't want to repeat too much information that you all know, but for those maybe who aren't experts in cuneiform or Assyriology, so we're dealing with these documents that were written by people in ancient Mesopotamia in the area which is now approximately modern-day Iraq. And as I think you know, this area was really important in the history of humanity for all sorts of things like the invention of writing, which is what we're looking at. Apparently also pretty important things like the wheel, math and astronomy, agriculture, and more. So we're really interested in learning what we can about how these societies worked and what they were talking about. And in order to unlock that information, we need to actually read what they wrote down. So in particular, writing was invented by the ancient Sumerians, which started out actually as pictographs, but over time it became more stylized, and it was impressed on clay, and that's going to be important for what we're talking about. This was probably the first time writing was invented in human history, and it was adapted by all these other civilizations who wrote in various different languages, but using the same basic writing implements and style. And it continued to be used for a very long period of time. So we're dealing with a huge corpus of texts. We have a lot of data, but data where we don't necessarily know immediately how to read it. So cuneiform was impressed into clay tablets. It looks kind of like these wedges. So from what I understand, they used something that was sort of like a chopstick pressing into clay. I really want to try doing this myself sometime. So, and what's interesting, I'll also say I have a bit of background in learning other languages. I learned Japanese for a while. I was really surprised by how similar the actual structure of the language is to Japanese. So it's actually a logographic or logosyllabic writing system because some of the characters represent morphemes, like units of meaning. Some of them represent syllables, roughly, and they can be combined together. So the writing system itself is very complex, and there are a lot of different characters. And each character, just like in Japanese, actually, each character has many different ways it could be read based on context. In addition, there's also the challenge of the fact that the actual characters and maybe the ways they were used changed greatly over millennia. So there's a lot of variation. It's not this kind of standardized thing. And it was used for all these different languages, including Akkadian, which is a Semitic language, but one that's unique in a lot of ways, and Sumerian, which is the language isolate. So in a lot of ways, this was really diverse and very challenging to approach from a computational perspective. Now, what's interesting here is that the actual size of the corpus, meaning the number of texts that are available to us in raw form, is huge. From what I understand, it's rivaling Latin and Greek in terms of how many texts are available. But unlike Latin or Greek, I think the group of people who can read the text fluently is fairly small. The majority of them, we have a scan, but no one's actually sat down and analyzed it and provided the full translation and transliteration and so forth. But we have a lot of raw data, so it seems like a promising area to use computational methods on. On the other hand, standard OCR just totally fails on scanned cuneiform for a lot of different reasons. I've already talked about how diverse it is, but there are other challenges that actually are just due to the nature of the way that it looks in the first place. So, like you can see, the text is really dense. Okay, it's not really like printed English where you have lines of text with white space in between them. The text itself is really dense, occasionally overlapping. Sometimes they go to the back of the tablet. You know, I remember in school when I'd get to the end of the line and I'd just start writing up. Well, they could actually flip the tablet over and keep writing, so they would do that as well. We have problems of the background, right? So it's not like a piece of paper where the background is pretty white. And with standard OCR, you might do like image binarization to turn the image into black and white. But if you try to threshold an image like this, you'll get garbage because the background itself is actually like colored and has darker and lighter regions. There's a lot of variation, which I talked about, and the writing system itself is complex. So you can't really just use a standard out-of-the-box OCR or even handwritten text recognition algorithm for this. So the idea of our Deeplomatics project is to apply deep learning to cuneiform diplomatics, which, according to this quote, is the study of the creation, form, and transmission of records, like from the word diploma. And so I just want to present two ongoing projects that we've been working on within this project. One, on a really important pre-processing task called line segmentation. And two, I want to present some preliminary results on dating tablets and how that correlates with the shape of tablets. Okay, so the first thing I want to present are our initial foray into line segmentation. How do we take a cuneiform text and split it into separate lines of text? So this is like a pretty typical task in standard OCR. You can see an example of this below. So here we have some text in Latin and it's line segmentation. And clearly this is like a lot simpler than it is for cuneiform tablets because the background is pretty uniform. So it's easier to tell where there's text and where there's no text. The text is definitely a little bit slanted and curved, but the standard line segmentation is able to deal with this pretty well. On the other hand, for cuneiform, we have this issue that the text is really densely packed together and the background is very non-uniform. So if I just look at a scanned tablet, it's actually very non-trivial to split it into lines. Classical methods don't work very well for this. By the way, sometimes when they wrote in cuneiform, they would also actually put these things called line rules on the tablets, where imagine you have a chopstick and you just press it into the tablet, kind of like lined paper that you would write on. But a lot of the tablets don't have this. And even when they do, the lines don't totally separate the text. The text is often written kind of on top of the line. So it's not so easy to split the text. Now here I have actually a manual annotation, which I believe I annotated. I'm not an expert in cuneiform, but I can tell where the lines are, or where the text should be separated. But we'd like to be able to do this automatically because this is really laborious. And imagine trying to read the entire tablet is pretty challenging, but trying to read it line by line is a lot simpler, maybe for a human and definitely for a computer. So line segmentation could be used for downstream OCR tasks, or even something that like an end user could use in order to browse and read tablets. And so our approach is to train a deep learning model to predict them using what's called panoptic segmentation, which I'll talk about in a second. Okay, so on the right you can see a manual annotation, but the question is, can we learn to do this automatically? And notice that we have cases where the text is both dense and also sometimes one wedge goes sort of into the region of where text on a lower line is. So you actually have to draw the lines really carefully. You don't really have a lot of leeway to play with them. Okay, so now let me talk about our approach. By the way, I'll say other approaches to OCR, like Denker et al., who are working on weekly supervised OCR for cuneiform, didn't necessarily predict the boundaries between lines. They found like the midpoint of the line and they're sort of hanging characters off of it. And that's one approach you can use. But our approach is looking at it from the other perspective and saying, well, maybe we can just separate the text into lines first, which is a lot easier than recognizing every character. And then once you do that, you have more simple data that it should be easier to then apply OCR to. So here's the idea. So here we are using supervised learning. We manually instance segmented lines for about 100 tablets. We are increasing the size of this, but right now it's a pretty small data set. And what's interesting is that this method actually works even when you don't have a lot of data, as long as it's representative of different eras and styles. So in the center, you can see instance segmentation for the tablet on the left, where someone had to sit and just draw the polygons. And now what we can also do is we can automatically skeletonize these instance segmentations, meaning imagine you draw a line through the center of every rectangle. So you can just take the vertical midpoints of every point inside of an instance, and then you also get a skeleton. And we'll use the skeleton as well. Okay, so we have these two things, the instance segmentation, which tells us where does each line start and end. And we also have the skeleton, which just gives a line through the middle of the tablet, or the middle of each line of text in the tablet. Okay, now, we're going to train a model to predict both of these. So if you think about it, predicting the skeleton is easier because you kind of only need to classify every pixel in the image. It's just binary classification. You're saying, is the pixel white or black? Is it in the center of a line or is it not in the center of a line? So that would be standard image segmentation or semantic segmentation. But on the other hand, that doesn't tell you where the lines start and end. And that doesn't really let you separate the lines from each other. We also want to predict the boundaries between them. So our model will also predict separate instances for each line of text. But we'll actually use both because predicting the skeleton is easier. And then when you do that, that also kind of gives you a guide that you can use to sort of adjust the instance segmentations. So because we're predicting both instances and semantic segmentation, this is what's called panoptic segmentation in computer vision. And so there are different models to do this. For our proof of concept, we trained mask-former, which is a transformer-based model that takes an image as input and then outputs masks. And each mask has a class, so we can look at the line instance classes, and we can also look at the skeleton classes and use them together. Okay, but one other thing, by the way, is because our data set is so small, we use really heavy data augmentation, which means that you take your ground truth data and you apply all sorts of random augmentations to it, like cropping different regions or stretching or squishing it or rotating it. And we found that's really, really important. This only works if you do very heavy data augmentation. But I was surprised to see that with such a small amount of data, we are actually able to predict something very meaningful as long as you augment. Okay, so now we have this model, how can we use it? So during inference, meaning once the model is trained, you look at its predictions for an image, and we found you can use this in a few different ways. First of all, we can actually just say, where is any text predicted? Not necessarily the individual lines, where is there any text? And that actually gives us a text detector, and we saw that that works really well. So on the right, you can see an example of just the text detections of this model. Right now, we're not looking at how it separates the text into lines. We're just looking at where did it find any text. And you can see that it gives us pretty accurate results. Right? Anywhere where the tablet is colored in yellow means that there's some cuneiform text that's present. And that locates cuneiform text in an image, but it doesn't yet tell us how to split it apart. Now, the next thing we can do is we can run line segmentation. And what works pretty well is that we found that this is really sensitive to resolution, meaning if you zoom in or out, it'll affect the predictions of the model. And the model usually works best when you zoom in on a smaller region. That makes the task easier. So what you can do is first you predict where is there any text in the image. That works pretty well. Then you look at each connected component of this and you zoom in on it. And then you predict line instance segmentation. So we're running this model multiple times. And in fact, it works even better if you zoom in on smaller regions, not the entire text at once. So if we zoom in on smaller regions of the tablet, you can see on the right, we get much more precise instance segmentation than when we just run on an entire fragment. But then the other issue is because we're predicting instance segmentation in each window, now we need to combine them together. We need to figure out how to glue different instances together. So the next idea is, well, we can use skeleton prediction for that. So the model also predicts the skeleton, like the midpoint of each line. You can see an example on the right. This is from a tablet. It was not in our training data. It's not really from the same distribution, but the model is still able to predict the midpoints pretty well. And so what we can do is then we look at all the chunks that our model predicted when we zoomed in, and we glue them together if they're on the same skeleton. Okay, so I'm just going to show some examples. I want to show you that it's pretty robust to ERA. We are in the process now of building a representative test set that covers all sorts of different eras and genres to show that this is really robust. But I'll just show some qualitative examples right now. So you can see here a tablet from the old Assyrian era. I have the dates here, but if you want more information on the history, you can ask Shai, because that's his area of expertise. But you can see it's able to pretty accurately split the text into lines. And if you looked closely, it's hard to see here, but you can actually see that the colors end right where the text ends, even if it's above one of the long lines on the tablet, which is pretty cool. Here's an example from the Middle Babylonian era, which is quite different, but we're still able to pretty accurately detect instances. Okay, here's from the Neo-Assyrian era. So imagine this could be used for a downstream OCR application, but it could even be useful to an end user, because if you're browsing a tablet and you're still learning Akkadian, it would be really nice to just be able to look at it line by line so you don't get confused by everything being smushed together. Here's a Neo-Assyrian example. The text format's a little different. Here they have these kind of boxes where the text was written, but it still segments the lines. And here's an example from the Neo-Babylonian era. Okay, so that's one project that I wanted to present. As I said, line segmentation, we found that with a pretty small amount of supervised data, but with the right methodology, we're actually able to learn something that's meaningful. It might be useful as its own sort of product, or it might be useful for downstream applications like OCR. So the one other topic I want to mention is tablet dating. This is also an important aspect of information we can get from a tablet. But here we're not even looking at the text on the tablet, we're looking at the actual shape of the tablet. So let me go back a little bit. Well, with Cuneiform, we have this physical object, but we want to understand it in context. It's really important to understand when was this written, what historical period. I said that the cuneiform itself varies a lot depending on period. So you can sometimes look at the text and understand when it was written, but it's often ambiguous. Apparently, scholars often disagree. And also, it would be really useful if we could automatically curate the tablets by era and then apply more analysis to them. So can we automate this process? And what do we need to date a tablet? Do we need to read the text? Or can we tell the date of the tablet just by maybe taking a 1-second look at it? So in order to understand this, we looked at a data set of scans of tablets from CDLI. They also come with metadata, so some of the tablets are labeled with dates, and that gives us ground truth that we can train a model on. The thing is, you can easily just train an image classifier to predict something from an image. But you don't always know why is the classifier making the decision, and that's something we care about a lot. So the interesting part of this project is not really just training a supervised model, it's actually the explainable AI trying to understand why did the model make that decision. Okay, so here you can see some tablets from different eras, and even for those of us who do not fluently read Cuneiform, I think you can very clearly see that all the tablets look different, right? So, but why do they look different? And does that tell us about when they were dated? Well, we tried just taking scans of tablets and training a standard image classifier, ResNet, and it worked pretty well. So here you can see that when we try to classify between 10 different dates, it's able to guess which date it is pretty accurately. So we got 87% accuracy. The data is imbalanced though, so I would say if you look at let's say the macro F1 score, that's more interesting, which is 73%, which is really high for a problem with 10 different classes, doing something that would seem to be pretty difficult. So it does much better than random. Even if you look at the mistakes that it often makes mistakes between eras that are close to each other. So the question is, okay, great, I can date tablets, but how? What's it actually looking at? Is it looking at something interesting? Or maybe the museum just saved all of the tablets from a certain era, in a certain format, and then that's boring, right? So, okay, so I thought, okay, well, it's probably looking at the text. But let's just check, okay? Let's just make sure it's really doing that. How will we check? Well, let's just make binary masks of all the images and we'll train the model on them. And then we should get bad results, right? Because the model can't actually see the text on the tablet. Does everyone agree with me? It shouldn't work? Well, actually it does work. So we're still able to predict the era pretty well. And I was really surprised when I saw this at first, because I was like, well, it's not even reading the text. How does it know what era the tablet is? It works really well. But then we realized, well, actually, there's this whole field of diplomatics, and they're actually classical works in this field using classical methods, not computational, that said that the tablet shape is really important. And that seems to be what the model is actually looking at. It seems to be that the model is actually looking at the different shapes, and they do correlate with the era as well as the genre of the text. We can also see if we look at the latent space of the classifier, meaning before it actually outputs the classification probabilities, you can look in a neural network at an intermediate layer and you get vectors, embeddings that represent each image, and you can look at how those cluster. And we see that the clustering also correlates to the historical intuition, as well as some visual intuition. Like all the green tablets are from a certain era and they all look kind of similar to each other, but we're trying to quantify exactly how. So our ongoing research project is doing the following. One, we're looking at generative models to analyze tablet shapes. So the idea here is that if you make a model that can actually generate new images, kind of like for people who know about DALL-E, imagine you have a model that can sort of make a new fake tablet or a new fake binary mask. Then you have control over that. Then you can look at how that correlates with tablet dating and how that affects what the classifier learns. And that gives us a way to understand what it's looking at. Maybe things that look more like fragments tend to be one era, and things that look more like big squares tend to be another era. And we're also looking at how to disentangle the effect of tablet shape from text style, because if you can predict era from shape and you can predict era from the text, you can look at how correlated are those two things and what independent effect do they have. And so that's an ongoing project, and I guess stay tuned, follow us on Twitter and so forth for more information about that. So those are the projects I wanted to cover. In conclusion, we're using state-of-the-art machine learning methods and computer vision and NLP to understand the ancient past. Existing OCR fails, so we have to develop new things. And in our Deeplomatics project, we have these different lines of research, especially line segmentation and tablet dating, that are making previously unanalyzed cuneiform tablets accessible. So that's everything that I wanted to cover, and I guess questions will be afterwards. So thank you, everyone.